In this video, we're going to discuss carbocation rearrangements, specifically 1,2 hydride shifts and 1,2 methyl shifts. So the idea here is that when we electrophilically add a proton from a strong acid creating a carbocation, we'll initially form it at the Markovnikov carbon, which here would be the secondary alkyl as opposed to the primary alkyl position. But after we form that initial carbocation, we want to pause and check for rearrangement. In this case, if I were to shift over a hydride, that is to say I shift over the hydrogen with its electron density, that would neutralize the former positive charge on that carbon, but then create a carbocation at the carbon from which I shifted the hydride. Now notice as we do that hydride shift, we form a tertiary alkyl carbocation, which is more stable than the original secondary alkyl carbocation. Rearrangement will only occur if doing so increases stability, which here it does. It has. No rearrangement would be observed, however, if there is no added stability because of the rearrangement. Now, we want to consider that rearrangement because the major product here is obtained through that rearranged carbocation structure. In this example, we've looked at a 1,2 hydride shift. Now, we can also do 1,2 methyl shifts, and I often get the question of how do I know if it's a hydride or a methyl shift? And the simple answer to that question is if the adjacent carbon position, where we potentially rearrange to, has a hydrogen, then it will be a hydride shift. If there is a hydrogen, it will be a hydride shift. Okay, 1,2 hydride shifts. Then we have 1,2 methyl shifts. Tracking with you. Let's electrophilically add a proton to create the initial Markovnikov carbocation, that is secondary alkyl. At the adjacent position, it's quaternary. Now, there's no hydrogen there, but there is a methyl group. Because there's no hydrogen, it would not be a hydride shift. Instead, here, we do a methyl shift. That is to say, the methyl group with its electrons move to the position where the former carbocation was, neutralizing that carbocation. But because we move the methyl group with its electrons at the carbon from which it shifted, we now see the positive charge being located there. Rearrangement has led to added stability, therefore it would be spontaneous and favorable. The major product would then be obtained through that rearranged carbocation structure. So kind of the key is anytime you're going through a carbocation mechanism is to pause and check for rearrangement, and will only rearrange if doing so leads to more stability. Now what that means is if this was, say, your initial Markovnikov carbocation, we could have a rearrangement here doing a 1,2 hydride shift, and doing so would relocate the positive charge to the secondary benzylic position. Now we haven't become more substituted, but we have become more stable. And I guess what I'm trying to get at here is rearrangement doesn't have to necessarily increase substitution, but we always will have to increase stability. If there is no added stability because of a rearrangement, there will be no rearrangement. In other words, if I had, say, this alkene pi bond react, I had initially formed the carbocation here. The adjacent position is now more stabilizing to the positive charge, so therefore I would not see any rearrangement. And to reiterate, the trick to know if it's a hydride or a methyl shift is if there's a hydrogen, it will be a hydride shift. But if there's no hydrogen at the adjacent position but there is a methyl group, then we'll do a 1,2 methyl shift.